example number 2, example 2.3.2 on mathematical induction. Okay, so we want to prove that. Prove by mathematical induction that 7n minus 4n is a multiple of 3 for all n belongs to natural number. So you need to recall back, what does it mean when we say that any numbers is a multiple of 3? Okay, so this is the equation that represent this one, which means you have 7 power of n minus 4 power of n is a multiple of 3, means it equals to 3 times k, where k belongs to some integer. Okay, so that is the meaning when we say that one number is a multiple of 3. Okay, so as usual, our first step is that we denote our general case, which is Pn. Okay, so Pn represent the statement 7n minus 4 to the power of n equals to the multiple of 3, which means it will be equals to 3 times k, where k here can represent any integers for all n belongs to natural numbers. Okay, so that is represent our statement Pn. Okay, so in mathematical induction, once we denote or we write our general statement, so we need to check on the basis of the mathematical induction. That means for the first case of our n belongs to natural. So means that we want to check for the case of n equals to 1. So P1. When we get the formula 7 power of n minus 4 to the power of n, when n is substitute equals to 1, it can be the multiple of 3 or not. That is what we are going to check. Okay, so simply we just substitute n equals to 1. So that means we have 7 power of 1 minus 4 to the power of 1. So we have what? 7 minus 4, which is equals to 3. And it is clearly this is a multiple of 3. Okay, so it indicates that P1 is true. Okay, so P1 is true. So settle for the first case. Okay, so we have shown that the first case is true. Then we proceed to the next case, which is our assumption step, which is PK. Okay, so we assume that the statement Pn is true for the case of n equals to k. So we let Pk be equals to 7 to the power of k minus 4 to the power of k, 4 to the power of k, and this will equals to a multiple of 3. So now, since we have used the symbol k to represent for any number n equals to k, so that to represent the multiple of 3, we use a different parameter. For example, this should be equals to 3m, for example, where m refer to any integers. That is definitions. So we assume this is the true statement. Okay, this is our assumption. We assume this is true. Okay, so the next one, we want to check for the case when n equals to k plus 1. So that means for k plus 1. N equals to k plus 1. So we know that if n replaced by k plus 1, so we will have this formula, which means 7 to the power of k plus 1 minus 4 to the power of k plus 1. This also will be a multiple of 3. So we want to check for that one. Is it the statement pk plus 1 will also equals to multiple of 3, which means it will be equals to 3 multiplied by some integers. So how to do that one? We are going to apply our step assumption just now, which is the step in pk. Whenever you have 7 power of k minus 4 to the power of k, you can replace that one by 3m. Or you can manipulate from that pk to replace the statement that we are going to check for pk plus 1. Okay, so now we can see that the left-hand side of pk plus 1, we want to check whether the left-hand side, can it possible to become a multiple of 3. Okay, so 7 to the power of k plus 1 can be written as 7 multiplied by 7 power of k. Okay, and 4 to the power of k plus 1 can be written as 4 multiplied by 4 to the power of k. Okay, so now we want to check what we can do, or we can apply our assumption step. Okay, so we can see that I can replace the statement, or I can replace the term 7k and 4k from the assumption step. Okay, so we have what? 7 multiplied by, so 7 to the power of k, if you look into the statement pk here, 7 to the power of k is equals to 3m plus 4 to the power of k. So I can replace that one, 7k, I replace by 3m plus 4 to the power of k. Okay, so that's how we use that statement which we assume to be true. We can use directly, either you have the term 7k minus 4k, you replace by 3m, or you can rearrange from that statement pk itself. Okay, for example, I use here 7k, I replace by 3m plus k. Okay, and the second one, okay, we can see that we have minus 4k, right? So I can remain that one as minus 4 times 4 to the power of k. And I further simplified this one. Okay, so I will have 21m. Okay, so I expand this one. Okay, and I have plus by 7 multiplied by 4 to the power of k minus 4 times 4 to the power of k. Right? So now look at into the last two terms that we have here, which is we have 7 4 to the power of k minus 4 times 4 to the power of k. So it becomes 3. So we can see that we have 21m plus by 3 times 4 to the power of k. Okay, which this one is actually has a common factor of 3. Okay, so we have what? 3 multiplied by 7m plus 4 to the power of k. Alright, so 3 multiplied by 7m, so we have the bracket here. Okay, where 7m, m is what? M is the integer, and our k is integer, so that the things in the bracket is actually becomes another integer. So that we have 3 multiplied by integer. What does it mean? It means that 7k plus 1, which we have our left hand side here, we simplify to be this one, and so on. Then we show that this is equals to 3 times the integer, which means 7k, 7 power of k plus 1 minus 4 to the power of k plus 1 is actually a multiple of 3. So by that, we have shown that Pn is true for n equals to 1. Pn is true for k equals to n, for n equals to k, and Pn is true for n equals to k plus 1. So in all the three cases, by the principle of mathematical induction, we have shown that 7n minus 4n is a multiple of 3. Okay, so that is the second example. Thank you so much.